This is Benjamin Turner with Latticept. I'm the American reseller of M-STAR. I'm going to show you how to do a half-pipe jacketed reactor. So that's heat transfer in an agitated vessel. The first thing we're going to do is create the vessel that's going to hold our fluid. If we go underneath the tank, we should see cylindrical tank and then click OK. That'll pop a tank into the model. For this one, I don't want any baffles. I'm going to add those separately. I'm going to rename this to vessel. Next, I'm going to go to create static body, and this is for the baffles. I want to add them separately because I don't want to transfer heat through them. Click OK. I'm going to rename this to baffle. We're going to adjust the diameter here so it's not in the wall, and I'm just going to rotate it 45 degrees so it's not in my planes. Alright, sounds good. File, save this. Just going to overwrite one of these. Okay. So now that's set up for a tank with some fluid in it. Now I'm going to create a moving body for our impeller, and click on impeller, and then a high solidity hydrofoil. Click OK. Impeller pops in. We want to make it bigger. Set the diameter to 0.5 meter, shaft diameter 30 millimeters, shaft length 1 meter. Click OK. Alright, file save. So in just a few minutes, seconds even, we've set up a agitated tank with a moving body. I'm just going to adjust the rotation speed to like 57 RPM just to show you that we can change that relatively easily. And then I'm going to create a thermal field. Now we've added the thermal field to our model. I'm going to change the maximum temperature to 600 Kelvin. That's going to be the hot oil. I'm going to adjust the thermal boundary condition of the vessel to Nusselt number. This is our generalized Nusselt number correlation. We're not going to change any of this yet because next we're going to add surface conduction to the tank itself. Go to create static body conduction. It's going to ask which static body. We don't want heat transfer through the baffle, so we're going to select vessel. Click OK. And then it's going to ask us which mode. Well, we want surface because we're not going to use volumetric. We have a pretty thin wall. Click OK. Next is going to ask us our initial temperature, 300 Kelvin. That's fine. We're going to change the thickness here to 10 millimeter, which is about 3/8 of an inch for American engineers like me. This conductivity, heat capacity, and density are set to stainless steel, which is completely reasonable for a jacketed vessel. All right. Next, we're going to add the surface boundary condition. Now remember, we're going to do a half-pipe jacketed reactor. So we don't want to just heat the wall. We actually want to heat it like a coil. All right, so how do we do that? Well, we're actually going to add a coil that's going to intercept the surface, and wherever it intercepts the surface, that's where we're going to heat it up. So we go to create conduction surface boundary condition. It's going to ask which body, this vessel. Click OK. You're going to select existing faces. No, we're going to import from file or catalog. Click OK. And then we're going to go to miscellaneous and we're going to select coil. All right. Remember, this is where it intersects it. So I'm going to rotate this. Go to rotate 90 degrees. X 90, 90, 90. Perfect. Okay. Now that's not intersecting anything, so let's change the diameter. Should be 1.08. Now, in the pressure vessel industry, we typically use a 3-inch jacket, 3-inch nominal, so the OD is 3.5 inches, which correlates to 0.0889 meters. Okay, our OD is right. Now we need to adjust the coil diameter, 1.08. That looks right. You can see it intersecting the wall here. Looks like it's pretty good, pretty dead on. Next, coil pitch. Most of the time we use 5.5-inch pitch, which equals this, 0.14 meters. So that's about right. Now I'm going to increase this to about 7, maybe 6.5. Well, can't do that. How about 6? All right. So this is going to be the area intersecting the shell. We're going to heat it up. How are we going to do that? Now that we have our geometry defining where the intersection is with the wall, go back to surface boundary condition. Now right now it's set to a constant temperature, but we're going to change that to a heat flux CUDA expression. Okay. What does that mean? We're going to have to write a simple script for this. So first thing first, it wants Q dot. If we click here, we'll see the output is Q dot, and we want heat flux with units of watts per meter squared Kelvin, or excuse me, watts per meter squared for surface and watts per meter cubed for volume. But we have surface, so watts per meter squared. So first thing first, float H equals, let's just say 100, and that's going to be in watts per meter squared Kelvin. Okay. I'm going to change that to 1,000 because that's the outside heat transfer coefficient in the jacket, which should be pretty high. And then what's the reference temperature of the fluid? Well, it's going to be about 600 Kelvin. Again, remember this is for hot oil. All right. And then we're going to write just a simple expression, Q dot equals H times, well, reference temperature minus the surface temperature, TS. or in this case, just T. And you know that because you go to local static body and see that T. So if you click this, you can also just double click that, boop, it'll pop right in there. Click check code. What did it say? Blah, blah, blah. I forgot. I typoed that. Check code. Perfect. Now we've written a UDF. So now we've put an surface boundary condition with a heat transfer coefficient equal to 1,000 watts per meter squared Kelvin and a reference temperature of 600 Kelvin. It's going to use the actual wall temperature as the reference temperature to calculate the heat transfer. Click OK. I'm going to save this. Now let's go back over here to our thermal field. Now you can see the reference temperature is gone because we're using the actual wall surface temperature. And so we have Nusselt number. And we also have adiabatic for the baffle, which means there will be no heat transfer through the baffle. Up here under thermal properties, you can see that we're using constant temperature. These are water-like properties. We're not going to change any of this. I'm not going to set the expansion coefficient. I'm just going to click File, Save, and then I'm going to solve this. Yep, sure. Dump it there. Click Yes. Okay. I forgot to do one thing. I'm going to increase the output interval. This is statistics. We're going to leave this 0.01. This will spam us a lot, but that's okay. I want to create a lot of output just to show you this. Click OK, File, Save. One last thing, if we go to Vessel, click Edit Mesh. This is kind of a more advanced setting. Let's preview our mesh. See, this is kind of rough. Since we have some thermal conduction through this, I'm going to increase that by going to Mesh Option Presets and click on Ultra Fine. So now as our surface mesh, we've increased that pretty good. Click OK, File, Save. This is our lattice. Check Preview Lattice. View Preview. We can see that this is the voxelized volume space. Perfect. Close, solve, select this folder for output. Yes. And here we go. Off to the races. Now we should be cranking along here. We are zooming along. Okay. So while this solves, let me show you a couple things here and just in general. Go to check preview lattice. Let's go back and talk about the lattice again. Remember, this is lattice Boltzmann. So this is the lattice. We don't have a mesh. We have these voxels. It's very similar to a mesh, except we can do it much, much quicker because we don't have to. It's always regular and it's always Cartesian, so it's easy to do. On thermal field, you can do all sorts of different things. You can add, if you go into create, you can have surface conduction, you can have volume conduction, you can also have thermal contact if you have multiple parts sticking together, but we're not going to do any of that. Let's go back to the solver, and we can see we're already almost 2 seconds into this. I'm writing a lot of output, so it's actually even faster than this, but I'm dumping so much data just for an example. So I'm going to click Post, and while that's loading, I'm going to click on the solver. So in M-STAR, the only thing you need to pay attention to really is your min-max LB density. I can tell that it's okay. It's scrolling past really fast. But look here, we are just on an NVIDIA GeForce RTX 4090. This is a gaming desktop GPU. There's nothing fancy here. It's just like $2,000, okay? Click OK. Now we can see this is pulled up. Now you can see almost in real time how fast this is. So this is just showing you the impeller starting to spin, okay? And you can start to see the vortex there for them, the vortices. Pause this. Let's click on the vessel point data. And then I'm going to change this to temperature. All right. I'm going to turn off opacity mapping because that's not helpful to us. Now you can literally see where the jacket was. And I'm going to change this to hot to cold just to give it some different colors. Now we're 2 seconds into this. So let's go back to the beginning. And you can literally see as we start to heat up the vessel, yeah, pretty cool, right? So now we're heating up. All right, that's great. So let's check on the actual heat transfer to the fluid. Let's turn that off. Let's take a look at our fluid here. So I'm going to change it from velocity to temperature. And over here, I'm going to change it velocity, temperature. I'm going to change all of them. So these are slices through. Okay. I'm going to turn the opacity mapping back on. And I'm going to adjust this just a little bit, just so we can take a look at this. Readjust this. We are about 6 seconds into this. You can't see too much heat transfer forming yet. But if we go click on thermodynamics and click, if we go to static body vessel and click create plot, we can see this is the heat transfer rate to the fluid. Right? This is the total vessel thermal heat transfer coefficient. Okay, so this includes the outside one that I defined of 1,000 and the inside one. So this is the overall heat transfer coefficient rate. And you can see that it's come, evened out pretty quickly. We have different temperatures for the layers because even though we're using surface conduction, we still have a gradient through the wall. It's thin walled, but we still have a gradient. You can turn that on just by, let me turn these two off. And then you can see here, like layer 1, 2, 3, you would expect them to be pretty close to each other, and they are. But you can see that there is definitely a through wall gradient, which is what you expect in a pressure vessel. So this seems to be working as we would expect. And as we continue, every time we click this button, we're loading new time steps, and we're getting farther and farther along. We're already 7 seconds into the simulation. And you can start to see heat forming at the wall, which actually it aligns pretty well because of the vortices. So let me turn this back over here and adjust this to the velocity magnitude. And turn off opacity mapping. Oops, that was the wrong plane. Turn that plane off. This is the one I wanted to see. Velocity. Enable opacity mapping. Okay, so we can start to see down here that we're starting to form. We might want to increase our velocity, our RPM in this case for the agitator, but this is giving you an example of how this works really, really quickly. So there's the velocity, and then save this. Let's look at the wall and the wall temperature here. I'm going to turn off the opacity mapping. I'm going to remap it. Okay, and jump to the end. So now we see we're heated up pretty well. Okay, so if we jump back to the beginning and watch it, yep, this is transient conjugate heat transfer on a GPU on a desktop in just a few minutes on the phone or on the webcam or whatever you want to call this. M-STAR is incredibly quick, and you can do incredible analysis very, very easily. That's it. Thank you.